To interpret the decisions of a large language model, we have to look precisely at how it weights its inputs. A new research paper from UC Berkeley and UC Santa Barbara, titled SPEX, Scaling Feature Interaction Explanations, proposes a method for isolating these exact mechanisms. A common baseline approach to model explainability relies on post hoc tools like SHAP and LLM. These tools use a technique called marginal attribution, which evaluates the importance of each input feature entirely independent of the others. This animated diagram illustrates a standard sentiment analysis task, where the LLM evaluates the phrase, "Her acting never fails to impress." Using marginal attribution, the explainer isolates the words never and fails, assigning independent positive scores to each token. By treating the inputs as isolated variables, marginal attribution misinterprets the semantic structure of the sentence. The model is reacting to a double negative, but the explainer attributes the positive sentiment to the isolated words. When the exact same output is analyzed by SPEX, the independent scores vanish. SPEX identifies never and fails strictly as a unified, interacting pair that generates the sentiment. A language model derives meaning by mapping complex interactions across an entire prompt. Evaluating features in isolation yields an incomplete picture of how modern AI actually reasons. Researchers have developed interaction indices, like FaithShap, to capture these exact connections. However, these tools hit a severe mathematical limit when applied to the long contexts used in modern language models. This layout shows the computational complexity dictating existing interaction models, omega of n to the d. Here, n represents the length of the input, and d represents the degree of interaction between tokens. Calculating every possible combination of tokens requires an exhaustive search. As the input length increases, the required computations multiply exponentially, creating a combinatorial explosion. In practical application, existing interaction indices exhaust their computational limits at around 20 tokens. Modern AI tasks routinely require analyzing context windows of 1,000 tokens or more. This suggests that solving the scaling problem requires moving away from the exhaustive search method entirely. Scaling explainability for long context models is a structural mathematics problem. To move forward, the architecture must find a way to bypass these exponential calculations. The immediate problem is identifying crucial interactions without running a calculation on every single possible combination. This visualization models the concept of natural sparsity. A language model might process millions of potential combinations, but the final output is driven by only a tiny fraction of those interactions. In mathematics and machine learning, this phenomenon is defined as Fourier sparsity. The useful data is concentrated in a few discrete locations. The vast majority of token interactions contribute exactly zero influence to the final output. In an exhaustive search model, these deadweight connections are still fully calculated, consuming massive amounts of compute. Previous explanation models assume a dense matrix, assigning equal computational priority to every potential node regardless of its actual utility. The reality of sparse data alters the problem. We no longer need to calculate every connection. We only need to extract a few strong signals hidden in the background noise. To find these sparse interactions efficiently, SPEX reframes the explainability task into an information theoretic signal processing problem. This diagram illustrates the first step. Instead of feeding standard text into the language model, SPEX queries the model using specifically designed masking patterns, selectively blacking out tokens based on a distinct algorithm. The underlying structure relies on BCH codes. These are algebraic channel codes traditionally used in the telecommunications industry to correct errors in data transmission. The researchers embedded the rows of a BCH parity matrix directly into these text masking patterns. By utilizing channel codes, the space of all possible text interactions is mathematically mapped onto what signal processors call a noisy channel. In this framework, the most important feature interactions driving the LLM's output act as a hidden message attempting to transmit through that channel. Borrowing tools from telecommunications allows SPEX to use highly efficient, proven decoding algorithms to isolate the answer, rather than relying on brute force calculus. The engine driving this extraction is the Berkeley-Macy algorithm, which decodes the crucial interactions directly from those masked query samples. This bipartite graph diagrams the decoding architecture. It separates the known observations on one side from the estimated values on the other. The left side contains the factor nodes. These represent the sampled observations pulled from the masked LLM queries. The right side contains the variable nodes. These represent the unknown estimated values of the sparse interactions we are trying to find. The decoding process runs on message passing. The factor nodes attempt to decode a singleton interaction and then send that estimate across the graph to the variable nodes. The system operates in an iterative loop. The variable nodes average the received data and pass messages back. This allows the factor nodes to refine their estimates until the entire graph reaches convergence. By isolating the math to these converging signals, the computational complexity drops from the exponential omega of n to the d down to tilde of SDN, where S represents the sparsity of the data. This algorithm proves that long context explainability requires intelligent architecture. By restructuring the math, we can bypass hardware limits entirely. The theoretical architecture translates directly into empirical performance across standard evaluation datasets like hotpot QA and sentiment analysis. Explainability tools are evaluated on a metric called faithfulness. This measures how accurately the explainer's reduced feature set can reconstruct the original output of the language model. This bar chart tracks that metric across the test data. SPEX achieves roughly a 20% improvement in faithfulness compared to marginal attribution methods. The method also yields strict efficiency gains. SPEX achieves higher interaction recovery rates while requiring significantly fewer training masks than previous indices like FaithShop. Most importantly, SPEX accurately identifies these interactions across contexts of approximately 1,000 tokens. This exceeds the 20-token limit that constrained previous interaction tools. These results clearly indicate that SPEX can reverse engineer LLM logic in environments where previous tools were effectively unusable. This mathematical accuracy gives engineers a practical tool for debugging specific reasoning errors inside closed-source models like GPT-4o Mini. To test this, researchers ran a modified version of the classic trolley problem. The prompt included a specific caveat testing reading comprehension over assumption. Pulling the lever may cause you physical strain. Across 1,000 evaluations, the model achieved an accuracy of just 11.8%. Analyzing the failure through a standard shape explainer yields scattered, unhelpful heat maps. Running it through SPEX isolates the exact two-part token interaction that led the model to rely on its pre-trained bias instead of the prompt's explicit rules. By isolating precise token interactions, engineers can pinpoint the exact contextual missteps written into a model's architecture. As LLMs are deployed into high-stakes domains, safety depends on understanding exactly how variables combine to influence decisions. SPEX provides a mechanism to map these combinations with mathematical precision.